Okay, so this is 3.5 continued, the section on implicit differentiation. And we're on example 3. We want to find the second derivative for x to the 2/3 plus y to the 2/3 equals 1. So let's start with the first derivative. We're going to do this term by term. So we're taking the derivative with respect to x of x to the 2/3. That's going to be 2/3 x to the 2/3 minus 1, which means negative 1/3, plus 2/3 y to the negative 1/3. And because y is a function of x, we need to multiply by y prime. And then the derivative of 1 is 0. Next, we want to solve for y prime. So y prime equals, that's going to be negative 2/3 x to the negative 1/3. All I'm doing here is moving this term to the other side, and then I'm going to divide by this coefficient of y prime, which is 2/3 y to the negative 1/3. So I'm going to write that as y to the positive 1/3 over x to the positive 1/3. And so here is my first derivative. So for the second derivative, I'm going to take the derivative of both sides again. So I'm going to do the derivative of y prime is y double prime. And then for this thing, we're going to need quotient rule. So let's go ahead and start low d high. So that's x to the 1/3 times the derivative of the numerator. So that's going to be 1/3 y to the 1/3 minus 1, so negative 2/3, times y prime. Again, chain rule. Minus, so that was low d high, this is high d low, so y to the 1/3 times the derivative of x to the 1/3, which is 1/3 x to the negative 2/3. And then all over low low, so that's x to the 2/3. Notice y prime is in here, and we know y prime, so we can change that and we can perhaps reduce a few things. So let's see, y double prime equals this first term. I'm going to bring the 1/3 forward, and then let me go ahead and write the x to the 1/3, y to the negative 2/3 times what y prime is, which is y to the 1/3 over x to the 1/3. And you can see that x to the 1/3 are going to cancel, and then the y to the negative 2/3 and the y to the positive 2/3 are going to combine. Then we have minus 1/3, and then that's it. We're not going to have anything special here. X to the 2/3, y to the 1/3, all over x to the 2/3. So the next thing I want to do to clean this up is probably put this into make this all into one fraction. So we've got the x to the 1/3 and the x to 1/3 canceling. So we're going to have y to the negative 1/3. Now, I don't want to forget about this 1/3 in front, so let me deal with it now. I'm just going to put the 3 in the denominator. And then for our next term, we're going to have minus, let me go ahead and finish the denominator so I don't forget that either. And then the next term, we're going to have just the x to the negative 2/3, y to the 1/3. And I'm going to go ahead and clean that up even further. If I take this fraction minus this fraction, that's what I'm going to do. So I'm going to have 1 over 3x to the 2/3 y to the positive 1/3. That's this first term. And then I'm going to have minus, there's a y to the 1/3 in the numerator, and then a 3. Well, the 3 is going to be there, but then the x to the 2/3 is going to become x to the 4/3 when we combine it with the x to the negative 2/3 in the numerator. And we could probably do more. We could get a common denominator, but I think this is a pretty reasonable answer. It's for the second derivative. My next example is if xy plus y squared equals 1, find the value of the second derivative at 0, 1, 0, negative 1. Okay, so then we're going to take the first derivative. So we're going to do this, of course, it looks so nice and simple, but it requires product rule. So I'm going to leave x alone and multiply by y prime plus 1 times y. So that's the derivative of x times leaving y alone. Plus 2y, don't forget your y prime, equals 0. Now we're going to solve for y prime. So that is going to give us, let's see, we're going to move this term over and then factor. So let me go ahead and factor the y from the x plus 2y, and then move this term, the y term, over to the other side. So then we can see that y prime is negative y over x plus 2y. Then we're going to work on the second derivative. So differentiating this term by term. So we're going to have the derivative of y prime is y double prime equals. And we can kind of choose to use quotient rule, or we could use product rule now that we have chain rule. I'm going to go ahead and use quotient rule. So we've got low d high don't forget the y prime, minus high d low. That's going to be 1 plus 2y prime. The derivative of x is 1, and the derivative of 2y is 2 times y prime because of chain rule. And then over low, low, so x plus 2y quantity squared. So now we just need to clean it up. So we do have y prime. Which is right here and right here. And so we can put that in, and then hopefully we can do more to simplify this. So I've got in my numerator, let's see, I'm going to have a negative 1 and a y in the numerator, and then I'm going to have an x plus 2y squared in the denominator. So is that correct? Let me see. Not sure why I put that. Let me erase that. I take it all back. Okay, so I'm trying to put in the y prime here, and actually what's happening is this denominator cancels with this numerator. So I really just get, I better write it out just to be sure. Okay, so I'm going to write this negative in the front, x plus 2y times y prime, which is negative y over x plus 2y. And try to make my y not look like a 4. Okay, and then this is minus, I'm going to go ahead and resolve all these negative signs here, so this will be plus. And then it's going to be y times the quantity 1 plus negative 2y over x plus 2y all over x plus 2y squared. So now I'm going to move over here. So let's see. We've got this term right here. These cancel, and we just end up with positive y plus. For this other one, I'm going to go ahead and distribute that y. So I'm going to have y plus y minus 2y squared over x plus 2y. And then this is all over x plus 2y quantity squared. So if we want to clean that up even further, I'm going to put 2y times x plus 2y for common denominator. I guess I'll do this, minus 2y squared times x plus 2y, and then all over x plus 2y squared. That seems a little, let me double check what I'm doing here. So let me see. So the y plus y gives us 2y, and then we have plus, or we have minus this. So what I did is I multiplied this term by one more of these to put it over squared. And then it's already over squared. So then this denominator should be x plus 2y to the 4th power. And that should work out. Okay. So the question, however, was asking to find the value at a specific point. So I'm going to write this as, whoops, d2f dx2, so second derivative, evaluated at x equals 0, y equals negative 1. And that's this point up here. And, you know, upon looking at this, I'm going to use this one because with real numbers, I think that this one's easier. And then if I made any mistakes on this one, it won't screw up my answer. So I'm going to go ahead. I wouldn't really like you to leave your answers like this with a nested fraction, as we discussed before. But I think in this case, if we're going to substitute in just these numbers, it'd probably be easier to deal with this one than this chunky thing. Okay, so y plus y, so negative 2 minus, and then I have 2y squared, which is just 2, over x, which is 0, plus 2y, so negative 2, all over x plus 2y again, which is negative 2, but squared, so all over 4. And so I'm going to have negative 2 plus 1, so negative 1 over 4. And I just checked, and that's the correct answer. So, just a quick bit here on tangents and normals. Which we've talked about tangents a lot, and we've also talked about normals, not a lot, but we have talked about them. So if I have some curve here, and I'm looking at just some random point on our curve, then tangent, we're all pretty familiar with. Whoops, there's my tangent. The normal line is perpendicular to the tangent, so a normal at a point is going to look like this. And they are 90 degrees apart. So for example 5, find the equation of the tangent line normal to the given curve, the tangent line and the line normal to the given curve at the given point. So find the equation of the tangent and normal. Here's our function, or our equation. So x squared cosine squared y minus sine y equals 0. And in order to actually come up with the equation of the tangent line and the normal line, we need it at a specific point. So we're going to do this at 0 pi. You can verify that if you plug in 0 for x and pi for y, and sine of y is 0. So we do, this point is on curve. Okay, so let's take the derivative, and the derivative will give us the slope. So for the tangent line, we need the slope, which is going to be the derivative evaluated at 0. I could say the derivative evaluated at 0 pi, which might be more accurate. So we're going to have two variables. And then the point is going to be 0 pi. So when we finish finding the derivative and evaluating it at that point 0 pi, then we're going to use point slope with this point with 0 pi. So let's find the derivative. So here's my function, or I keep calling it a function when it isn't, with a inverse sine. Actually, this one, no, because there's another cosine y, so it's not a function. So we want to take the derivative of this first term, and you can see there's a product. So we're going to have to do, let's leave x squared alone, and then take the derivative of cosine squared y plus 2x times just cosine squared y. I'm saving this one to do on the side. And then the derivative, whoops, I almost forgot my second term here. So I need the derivative of sine of y, which is cosine of y, times y prime. And then the derivative of 0 is still 0. Okay, so for cosine squared y prime, so this is cosine y squared. So we need chain rule. So we're going to get 2 cosine y. We're reducing the power on cosine y by 1, so it's just to the first power, times the derivative of the inside function, so that's negative sine y, times y prime because of chain rule. So let's put that in here. We've got negative 2. Let me take the parentheses off of all of it. Whoops, wrong one. And I managed to somehow. Okay, so I'm going to have negative 2 x squared cosine y sine y y prime. And then let me double check and make sure I didn't miss anything. I don't think I did. Plus 2x cosine squared y minus cosine y y prime equals 0. I can put parentheses around this and around this just to make sure that it doesn't look like y prime is caught up in the argument. there's our y primes. So if we solve for y prime, we're going to get negative 2x cosine squared y over negative 2x squared cosine y sine y minus cosine y. So that cleans up a little bit. Again, we're going to evaluate at the point, so we don't need to clean it up a whole lot, but I am going to get rid of all those negatives. And I am also going to factor out, if you guys can see, the cosine y is happening in every factor. So that will be eliminated, and then the negatives as well. They're everywhere. So we've got 2x cosine y over 2x squared sine y minus 1. Okay, that should be a plus 1. And according to my notes, it's supposed to be a negative 2x in the numerator. I have to see. I don't think so. You can correct me if I'm wrong. But I think I was careful enough. I know this negative up here is coming from the derivative of cosine. So that is fine. And I don't see anywhere else where that might not be right. So let's go ahead and move on. We want to evaluate that at the point 0 pi. And as it turns out, we've got 0, not over 0, so that's good, but 0 over 1. So we just get 0. So I guess the negative wouldn't have mattered. But I'm pretty sure I kept track of the negatives pretty well. So what is our tangent line? If we do our y minus y1 equals m times the quantity x minus x1, then what we have is y minus pi equals 0 times x minus 0. So y equals pi is our tangent line. So if our tangent is a horizontal line, again, we're looking at the point 0 pi. So here's our point 0 pi. Then the normal is going to be perpendicular to that. So that means it's going to have not zero slope, but undefined slope, and it's going to be of the form x equals something. It needs to go through this point, so that's going to be x equals 0 for the normal line. So here are our solutions. And if you're curious, you might want to graph that on GeoGebra and double check and make sure that everything works.